Okay, so welcome to the actual lecture for today. We're going to talk about the project today, and it's essentially two parts. First, I would like to talk a little bit more about the physics, both the lid-driven cavity, but then also a little bit about the Rayleigh-Benard convection case. That is the second part of the homework, which is compulsory for the PhD students, so for SG 3114, but may be interesting anyway for all the other students to do, or at least to kind of understand what the basic idea of the code would be. And once we have gone through the physics, which maybe is the first half an hour for today, then we will look at some of the implementational issues in the project, some of the choices that we made on how to implement certain terms, and this will then be mainly during the second hour. So I hope that you have all had the chance to at least very briefly look at the project description. Have you had the chance to do that?
Yes.
Okay, very good. So we will just I will pick a few aspects that I think are important, and then we will discuss those today. And as I said on Thursday, when there is general questions, of course, I particularly also invite questions to the project. So if something is unclear for the project, that we can go through that and discuss that in more detail. Okay, so what we have, where we have the point that we have reached from last time, continuation. So we have done the non-dimensionalization of the project. So we have essentially introduced a reference, a reference length, which was essentially the height, Ly. We have introduced a reference speed or a reference velocity, which was the lid velocity. And we have characterized the fluid as usual with the viscosity. And this then allowed us in the first hand to define a Reynolds number, which was U lid times Ly divided by the fluid property, the viscosity. And it also allowed us to kind of sketch our flow field or our geometry in terms of these non-dimensional variables, namely we defined an origin of the system. We have a coordinate system x and y, and then we know that this length here would be 1. This length would be 1 in the non-dimensional form, because we used the Ly as the reference length, and for at least the first problem, we look at the square cavity, so it's 1 and 1, and then we also have the speed here on top, which has a velocity of 1. Okay, so this is our non-dimensional case. I would just like to add one more comment regarding the Reynolds number. Of course, you know the definition of the Reynolds number as being a speed times a length divided by the viscosity. Of course, if you figure out the dimension of that, you will see that this has dimension of 1, so it has no physical dimension. That's why the Reynolds number is, of course, an ideal scaling parameter for us. But as you know, and Arishir has also discussed, the physical relevance of the Reynolds number lies in the fact that it actually gives you a ratio between inertial forces and viscous forces. Of course, the viscous forces are essentially determined by the viscosity, but it's maybe less clear why it becomes U lid times U Ly for the inertial forces, or not for the inertial force, for the numerator of the Reynolds. Actually, the way that you may rather want to think here is that you actually try to estimate what the inertial and the viscous forces really are. And in order to do that, you can essentially just go into the Navier-Stokes equations and see what is the unit of the inertial terms and what is the unit of the viscous terms. And if you do that, you will see that the inertial forces, essentially coming from the nonlinear term, which is u times du dx, that essentially is u squared divided by a length scale. U squared divided, u times du dx gives you u squared divided by L in terms of dimensions. So that would be the inertial part. And the viscous part, if you again just look in the Navier-Stokes equation, which is the momentum balance, so you have actually forces in there, you will then see that the viscous term will be something like the viscosity times the velocity and the second derivative of that, so divided by L squared. So that would be the viscous part. And of course, now you directly see, if you simplify that, you see that one velocity goes away, and so you have a u left, then you have the L squared and one L, so you have an L here, and you have a viscosity down here. So that's kind of the way that you would need to think of about the Reynolds number. It's inertial forces divided by viscous forces. Okay, so now we have our cavity, non-dimensional, one a square with a size of 1 and a velocity of 1 on top, and described by the Reynolds number. Now, essentially, for the physical description of the lid-driven cavity, that's it. Now we have it simplified as much as we can, a unit, square, and a Reynolds number, and now we can start to implement it. And then we will get a result. The code will give you a result as a function of Reynolds number, and you can then analyze these results. This is what we're going to discuss later on, what we would actually expect from the case. Right now, I would actually like to go on and discuss a little bit more the second test case, namely the Rayleigh-Benard convection. Also there, starting with a short case description, and then describe also how to do the non-dimensionalization, and then come up with the same non-dimensional formulation as we have done just now for the lid-driven cavity. So let's now look at the Rayleigh-Benard case. Rayleigh-Benard convection. So the basic idea there is that what you look at, or what the flow case is all about, is that you have two walls, one here, an upper wall, and a lower wall, and consider them, at least for now, to be very, very large or infinitely large. So that's the basic idea. And then you have, of course, a fluid inside, and you have two different wall temperatures. So you can say, if you now start actually with the physical definition, you have a temperature here, which is the T low, and no, not T low, T bottom, and T upper. So a wall temperature on the top and on the bottom of this case, of this domain. And the two walls, they're separated again by a certain height, which I can call to be the length of or the distance Ly. And now the idea is that we choose the two temperatures in such a way that the buoyancy force that is present in the fluid will counteract the kind of the damping force of the viscosity. And at some point, if you increase the bottom temperature in such a way that the buoyancy force becomes stronger than the viscosity. In that case, so again, imagine that T bottom is larger than T upper. That means that fluid particles here at the lower wall, they are heated up. As you know, if you have a higher temperature, the density would go down, and that, as I said, gives you rise to a buoyancy force. So essentially, this fluid particle here wants to somehow go up. At the same time, if you have a fluid particle or volume of fluid at the upper wall, you have a lower temperature. So that means that the density goes up, which means that this fluid particle would like to go down. And if, as I said, if this temperature difference is large enough, then this buoyancy force will actually overcome the restoring force of the viscosity. And what you will get is kind of a circle of, or a vortex here of fluid particles that constantly go from the top to the bottom and from the bottom up to the top. Of course, there will be not just one vortex, there will be actually a second one here, which rotates in the other direction. There may be another one here, which rotates in this direction, and so on. So there will be a whole range of what is called convection cells. Arising when you have enough of this buoyancy force. So if the temperature difference is large enough, and it's exactly this flow structure, this flow that we would like to simulate. Now, as I was saying before, we have a physical dimension of which is the height of the channel, so the distance between the two walls. But actually, it also turns out there will be, as a simulation result, there will be also a size of these vortices. So you can think of this to be an array of similar or of pairs of counter-rotating vortices, which then give rise to a certain wavelength. You know, this vortex is the same as this, so you can define a wavelength or a distance between these pairs of vortices. And this distance here I would call now to be lambda x, if x is the coordinate in the lateral direction. This lambda x then can be defined as a wavelength, or also as a wave number, 2 pi divided by kx, for instance. So essentially, this is the case that we would like to simulate. Now, we have a slight issue with the code that we're going to implement. Namely, we are not able, or we would be able, but it's not implemented in that way, to have infinite boundary conditions. So what we do is actually we set here on the side also a solid wall, and also here we set the solid wall. But in order to make it as similar as if you had very walls that are very far away, we consider here to have adiabatic walls on the side. Adiabatic means that the gradient of the temperature is 0 at that well. So there is no heat flux that goes from the domain out through that wall, or vice versa. So that's one way of kind of imitating a very large domain. So this is the second case. What we need for that is, of course, to add another equation to the Navier-Stokes equation. So we're not only considering the velocity, but we also need to consider the temperature as an additional quantity that is being transported. And how to do that is explained in the manual. Essentially, you consider the temperature to be a scalar. So you solve another transport equation for a scalar with the usual terms. You have a convective term, you have a viscous term. The only difference is that for a scalar, you do not have a pressure term. There is no pressure as part of the scalar transport equation, which makes the scalar equation somewhat simpler than the velocity or the momentum equation. And then you also need to implement the buoyancy forcing as indicated in the manual as well. So you need to have a buoyancy force in the vertical direction that depends on essentially the local temperature. As I was saying, the temperature changes the density, and the density then gives rise to a buoyancy force. And this is can be approximated with something that is called the Boussinesq approximation. Boussinesq approximation. That's one way of implementing into the equations the effect of buoyancy in a straightforward way. Okay, so this is the flow case, still written in a kind of a physical way. Of course, now we also need to make the transition from the dimensional physical setup into our preferred non-dimensional setting that we like so much in fluid mechanics. So how can we now non-dimensionalize this Rayleigh-Benard convection? I mean, in the end, it's the same thing as before. We need to define somehow length and velocity scales, and then we need to find, or we need to scale the equations in such a way that we actually get a parameter out that can be used for the dynamic scaling of this problem. So if we just start with defining a length scale, well, I think that is actually quite straightforward. I was mentioning before, these two walls are separated by a height Ly, and I think that is really the imposed length scale that you have in the problem. That's kind of the outer length scale that you have. So Ly as a length scale is certainly an appropriate number. Of course, now you need to keep in mind this is now it's not a square cavity anymore as before. For the lid-driven cavity case, this the Ly is much smaller than Lx, maybe a factor of 10 or so smaller. Okay, so we have a length scale. Now, the next question is, okay, what is a good velocity scale? How can we define a velocity scale in this for this case? And now this is not as simple anymore, because for the lid-driven cavity case, well, it was kind of straightforward. We had a lid velocity, and obviously this is our reference velocity. But in this case, we actually do not have a clear velocity scale given, but of course we need a velocity scale so that we can scale the velocities in the momentum equation. So I guess if we just start to write that down, we realize that the flow is driven by the buoyancy force. It's driven by buoyancy. So that means we somehow need to find the velocity. So define a velocity that somehow takes this buoyancy into account. Define a velocity based somehow on buoyancy, which in the end can be considered as being kind of a ratio or something that's based on diffusivity, thermal diffusivity, and advection. So based on diffusivity and advection. Now, kind of the same idea here that we can think of is we can introduce some time scales that define diffusivity and advection, and time scales for the diffusivity somehow needs to be related, of course, to the thermal diffusivity kappa. And if you look at the dimensional analysis, you will see that L squared divided by kappa, and I mean this would be our L squared here, the reference length. This will have the unit of a time. So this with kappa being the thermal diffusivity. Okay, so this is a time scale, and of course this together with the length scale, if we now look at the convection a time scale from convection would of course be something like L divided by the velocity. Assuming that if you have your cavity here, you have this is your length L. Now the question is, okay, what is a time scale that relates to convection? Well, if I want to go from here to here, my velocity is essentially the length, or my time scale is the length divided by the velocity. That gives me a time scale. Now the idea is that we would say that for the definition of our velocity scale, we set the time scale from diffusivity to be the same as the time scale from convection. So we essentially set that these two time scales would be the same. So essentially L divided by U would be L squared divided by kappa. Oh, no square here. And of course, that gives me now, if I solve this for the velocity, an idea what my reference velocity could be, namely kappa divided by L. And now what is this? Well, this is a velocity scale that we can call a convective velocity scale, because it's defined based on the diffusivity and the convective length, so the height of the box. And this velocity scale actually has a name, or not a name, a symbol that is called UK or U kappa. And this is the velocity scale that we're going to use for the Rayleigh-Benard case. So we use this velocity scale to non-dimensionalize the equation. Unfortunately, we're not there yet, because now for the Rayleigh-Benard case, there is a third quantity that we need to non-dimensionalize, and that is actually the temperature. We have T bottom and T upper as two physical temperatures in Kelvin or Celsius or whatever quantity. So we somehow need to also there find a way of non-dimensionalizing that. And for the temperature, the typical way is to use the difference between, so the delta T between the two walls as the scale. So temperature non-dimensionalization. The idea there is that a non-dimensional temperature theta would be the temperature minus, let's say, the upper velocity divided by delta T. And this delta T could be T lower minus T upper. That's the typical way of how to non-dimensionalize a temperature. So you scale it with delta T and you remove the lower temperature from the, so you subtract the lower temperature so that you have something in the end. In this case, it would go from 0 to 1. You would have 0, so theta being 0 on top, and the theta being 1 on the bottom. That's the typical way for a temperature normalization. Okay, now that we have introduced length scale, velocity scale, and the temperature scale, now the next step would be to rescale the equations using those quantities, and then to identify what is the actual parameter, what is the actual non-dimensional parameter that can be used to scale the dynamic equations, so the Navier-Stokes equations in this case. I'm not going to do that right now, but the final result, in a similar way that Arashi did for the Reynolds number in the first or second lecture, in the same way, if you use these scalings, you will actually find that the flow is not defined or is not dominated by the Reynolds number, but rather by the so-called Rayleigh number. So the governing non-dimensional parameter will then become the so-called Rayleigh number. The Rayleigh number is nothing else than trying to characterize, now in this case, the effect of buoyancy divided by the viscous forces. Very much in the same way as I explained before for the Reynolds number. Now, in terms of numerical values, of course, now we need to think a little bit, what are the quantities, the physical quantities that need to come in? And if you think about that, you will get G as the gravitational acceleration. We have alpha as being the thermal expansion coefficient. We have delta T as being the temperature difference, and divided the whole thing divided by the viscosity, this velocity scale that we have just introduced, and the whole thing divided by L squared. And if you now check the dimensions of this, you will see that in the end, this will be a non-dimensional number. And as I said, this represents buoyancy divided by viscous forces. Okay. So what is now the relevance of the Rayleigh number for this particular case of the Rayleigh-Benard convection? Well, people have studied this flow case for many years, and in fact you can study it yourself in a slightly approximative way, but you can study it at home also in the kitchen by essentially you know, in the frying pan when you heat oil. You can also see, or water in a pan, you can see that initially when you put cold water on the stove, nothing happens. But as soon as you start to increase the temperature, so if you turn on your stove and then you wait for some time, at some point you will see that you will get a convection in the flow in the pan. You will see that most probably by just looking at bubbles that are created, and then they at some point they start to move around in the pan. The realization that there needs to be a certain temperature difference that the whole thing comes into play actually means, if you translate it now to the non-dimensional number of the Rayleigh number, it means that most probably there is some critical Rayleigh number that actually is needed to start the whole process. Because it's kind of easy to understand, well, the temperature is here, but the temperature difference here, but of course the gravitational acceleration also plays a role. The distance between the walls perhaps also plays a role, the viscosity, the expansion, and of course UK where you have the diffusivity as well. All these quantities kind of go in to determine when, you know, that this convection starts. And that also shows kind of the power of non-dimensional numbers, because you can encode all these different effects in one single number that then is useful dynamical scaling. So what people have realized, as I was just saying, that there needs to be a certain critical Rayleigh number for the whole thing to actually start. And then, of course, the idea was, yeah, if there is a critical Rayleigh number, maybe one can calculate it. And during the last of the 18th century, people were then, or the 19th century, the 1800s, people were starting to look at that with different mathematical tools. And it was, in fact, Rayleigh that was the first person that could actually solve that problem and come up with a prediction of what this critical Reynolds number is. And he used something that is called the linear stability theory, which will not go into details in this course, but there's other courses where you can essentially study that. The basic idea is you linearize the Navier-Stokes equations and then you solve an eigenvalue problem, which then gives you this critical Rayleigh number. What he has then found is the following, that you can essentially draw a diagram like this. You can draw on this axis the Rayleigh number, and on this axis you can draw the wave number kx. Remember, wave number kx was this guy here, so the size of the structures that arise. And in this diagram, one can then calculate that there will be a curve that perhaps looks like this. And this is something that's called the neutral stability curve. And you can see that, or what one can then calculate is that all the combinations of Rayleigh and Kx that lie inside this curve, they would be unstable in the sense that the Rayleigh number is large enough so that the buoyancy force is actually large enough to win over the viscous force and to get the flow going. That is inside this curve, and outside it would be stable in a sense that buoyancy is not strong enough. Of course, now from this plot, you will see that there is a critical Rayleigh number, namely the point with the lowest Rayleigh number for which you have an instability setting up, or an instability starting. So that would be the critical Rayleigh number, and that is typically called RAC for critical Rayleigh number. And using mathematical tools and eigenvalue analysis, you can actually calculate that, and this critical Rayleigh number is 1708, and you can also calculate the corresponding critical wave number, and this critical wave number is approximately 3.12 in the typical non-dimensionalization. So this is exact results that you can do from linearized stability theory. And now what we would like to do is we would like to use our code, our little MATLAB code that we're going to develop, to see whether we can actually match this point, whether we can see that if we are a little bit below in terms of Rayleigh number, that nothing happens. I mean, the flow is what we would call stable. And if it's a little bit above, we would then see that the flow would exponentially grow and reach an equilibrium, a nonlinear saturated state with non-zero motion. And in fact, doing this type of checks that you validate your code against linear stability results, that's a typical way of making sure that an implementation in a code is actually correctly done. So we can validate our code against, I write now exact in quotes, stability results. I put it into quotes because it's exact for the linearized equation, but of course we're solving the nonlinear problem. So you need to kind of be a little bit careful when doing that, because you actually compare different methods. But if the disturbances that you put in are reasonably small, so that a linearization is appropriate, then of course we can consider these to be exact results. And this is what we're going to do with our codes to make sure that our implementation or our method is sufficiently accurate. And of course, I will maybe take away some of the fun, but of course, that it will work out. If you implement everything correctly, you can reproduce this bifurcation point up to, I guess, on the order of 1% accuracy, or maybe even less, meaning that our implementation is correct, and meaning also that we're actually solving the Navier-Stokes equations in the correct way. That also explains why we believe that this Rayleigh-Benard case is actually a very interesting case for us to simulate, because it combines, of course, the interesting aspect of having a scalar, a temperature in the domain, but also it provides us with an exact check on the accuracy of our code, because we can actually validate something. Okay. So this is what I wanted to say about the physical aspects of the project. So it's these two cases, the lid-driven cavity and the Rayleigh-Benard convection case. Both have their own benefits, and both of them are actually they are used quite frequently in testing, simple numerical methods. So it's not any strange cases. They all have their difficulties or issues. So for instance, for the Rayleigh-Benard case, as we'll also see in the results, we have this issue of the side walls, which just need to be far away from the wall. And in the lid-driven cavity, we have the aspects of these corners here. We have not really talked about that, but you can imagine that you have a still wall here, a wall that is still, and then you have here a high velocity that comes. And of course, in that point, in the corner point, you will meet a high velocity with a solid wall. And of course, that's from a kind of a physical point of view, this would indicate that something needs to happen. There is a singularity there, which if one would do more careful studies, one would need to regularize that in some way. For us, in our MATLAB code, we just ignore it. We just put the boundary conditions from the lid. But that's a slight issue that one would need to consider. But anyway, these are the two cases that we would like to study. And as I said, I think both of them are kind of interesting in their own way. Good. But then I guess the next step now is we need to actually see how we implement our code. So what numerical method that we're going to do. I would like to do that in two steps. First, I would like to introduce the numerical method. That we're doing, or kind of the solution procedure. And then in the second step, I would like to talk about the discretization. So I consider first the way of how we do the time advancement, so how we in particular calculate the pressure, and then in the second step, we discuss how to do the discretization. So that means if you don't have any more questions regarding the physical cases, so the lid-driven cavity and the Rayleigh-Benard case, if not, then I would like to start with discussing briefly on a numerical level what the steps are that we want to do to come to our solution. So what we're solving here are the 2D incompressible Navier-Stokes equations. That's what we want to solve. And I just start with writing them down. I write them down in a slightly, maybe not fully a standard way, because I would like to kind of separate various terms, because we will treat them in different ways. So I'll start with the time derivative. Then we have the pressure gradient. I write the pressure gradient directly after the velocity. And then on the right-hand side, I will write everything else. So I have a nonlinear term. So duu dx plus duv dy. And then I have the viscous term, 1 over Reynolds times d squared u dx squared plus du d squared u dy squared. And then I have some forcing terms. So this here is the x momentum equation. Then of course I have the v momentum equation exactly in the same way. I have dv dt plus dp dy. That is the same as duv dy dx, sorry, dx plus dv v dy plus 1 over Reynolds d squared v dx squared plus d squared v dy squared plus fy. So these are the two momentum equations that I would like to solve. Of course, I also have the continuity equation that I need to solve. So the essentially du dx plus dv dy being 0. But as we discussed, or as others here discussed with you, the problem with the continuity equation is that there is no time derivative here, really. So we cannot just kind of write it down as an additional equation. The continuity equation will rather serve as a constraint on how the time derivative of u and v may evolve, in a sense that we always need to make sure that the continuity equation is fulfilled in whatever way we time advance the u and the v momentum equation. So the continuity equation needs to be considered as a constraint on u and v as they evolve in time. So therefore, I'm not writing them down in exactly the same way as the u and v momentum equation. Okay, I see that it's now 2 o'clock. I guess we can take 15 minutes break, and then after after the break, we will then go through these various terms and kind of step by step describe what we will do in our code. And then once we have done that, we look at how it's in fact implemented. Okay, so therefore I would like to stop now for the break. Let's continue for the second hour today. Now we will talk about the numerical method on how to solve the Navier-Stokes equations, and then also in the second part how to implement it. So what I wrote down here is the Navier-Stokes equations, essentially in the way that we're going to solve them in our project. Now, why did I write it in this way? Well, the issue is exactly that we have on the left side here the time derivative, so the terms that we need to update, and the pressure. Why did I put the pressure also on the left side? Well, the thing is, we don't have an explicit equation for the pressure, as we discussed before the break. We only have the continuity equation that we can then, in some sense, abuse to calculate the pressure, because the continuity equation is a constraint on u and v that can be imposed onto u and v via a specific choice of the pressure. So therefore, we consider the pressure and the time derivative in some sense coupled, in a sense that we need to adjust the pressure in such a way that then together with the time derivative, we make sure that the divergence is fulfilled at all times. So therefore, I put the pressure on the left side as it will be calculated as part of the time integration. Everything else I have now put on the right side. In particular, we have the nonlinear term, we have the viscous term, and we have the forcing term. And I guess that's also kind of how we solve the problem. We first calculate the nonlinear terms based on the solution that we have at time step, let's say time step n, the old time step. Then we calculate the viscous term again at time step n, the old time step explicitly. We calculate the forcing at time step n. As soon as we have 1, 2, and 3 together at the old time step, then we know what we have as a forcing, as a force to update the velocity. And that means then I can go into step 4, which is solving the coupled pressure and time. And actually, this will be the 2 independent steps. So I'll call them step 4 and 5 together. And this will then give me, in the end, the result at time step n plus 1. So this essentially is the broad view of how I would calculate it. So if I do it a little bit in more detail, so the basic idea is, first I will calculate what is called an intermediate velocity, and I can call it u star. I can also use now the vector notation to say that this is actually u star and v star together. And this intermediate velocity, this I calculate based on my steps 1, 2, and 3. So essentially all the terms that are on the right hand side. So formally speaking, I can write like this: u star minus un as vectors divided by delta t. This is my steps 1, 2, and 3 together. So if I call this term here maybe to be n for nonlinear term at time n, here I would call it. I can say that this is 1 over Reynolds times L times un, with a matrix L which corresponds to the Laplace operator, and then I have the forcing term and call it f at time n. So I would now write here n at n plus 1 over Reynolds L matrix times un plus fn. This now would correspond to my intermediate velocity u star. And of course, you recognize here I'm doing the simplest possible time integration via an Euler forward scheme. Okay, so that gives me an intermediate velocity. This intermediate velocity u star has not yet taken into account the continuity equation. We have only taken steps 1, 2, and 3, but the continuity equation, so this constraint, we have not yet used. So that means we somehow now need to find a way of updating u star to a new velocity, which also takes the continuity and with that the pressure into account. So the idea now is to write the second equation, namely un plus 1 minus u star divided by delta t is, or I can write it with a plus, it's maybe more consistent with the equation, so plus g times p equaling 0. Now, what does this equation mean? Well, first of all, you can directly see I can combine these two equations, and then, by just adding them together, I can see that u star will disappear, and I will end up with essentially a discretization of the whole equation, including now also the pressure gradient. So the g operator here, that would be the gradient operator. So what I have done by writing it in this way, I have just split my time integration into two parts. One part when I have the right-hand side, and the other part when I have the pressure gradient. And this step here, as Ardeshir was also discussing with you, this is what is called a fractional step. Fractional step is because I break up the whole step into two parts. Okay. Now there's one question that remains here, namely how to calculate this pressure, because we need to have the pressure to be able to do this second step of the fractional step method. Well, there's one equation that we have not yet written down, and that is the divergence condition, so the continuity equation. Again, I can write that now like this, that I say that the divergence of un plus 1, so at the new time, actually should be 0. That is my additional condition that I have. And well, if I now try to combine that, well, meaning essentially I take the divergence of the second step, so taking the divergence of let's say equation star, So if I take that divergence, I can arrive to the following equation. Namely, I take the divergence, then I will see that dun plus 1, of course, is 0, and du star remains, and also d times g times p remains. So what I will end up with is d times g times p is L times p. Well, that's short for that, L times p, which is then the same as 1 over delta t times du star. So this one is then divergence times gradient. This will be the same as a Laplace operator. So what we see here is that what we have gotten here is a pressure Poisson equation. The forcing term is, as you can see, just the divergence of the intermediate velocity, and that gives me then the pressure. And this is what we call the pressure Poisson equation. And calculating essentially this, or solving this problem, that is my step number 4. So I calculate a consistent pressure with my specific intermediate velocity. And then step number 5 in my algorithm would be to actually use that pressure to update my velocity according to essentially this equation. So my step number 5 would then be correct the intermediate velocity with the pressure that I have just calculated. So that means my un plus 1 would then be u star minus delta t times g times p. And that is, as I said, that's the pressure correction, or you can also say a pressure projection. As Ardeshir was explaining, you project the intermediate velocity into the closest divergence-free velocity. There's various names for that, but the basic idea is you make sure that the intermediate velocity becomes divergence-free based on that. And then this un plus 1 is then my new velocity, which is now divergence-free, because I used a specific pressure that made this divergence-free. Okay, I would like to add, well, I think it's 3 comments that I would like to add. The first comment is about what is the actual time for the pressure. I avoided writing down here, a superscript n or n plus 1. Typically, what people write is that they say, that's kind of an implicit way of solving the pressure. So this would be Pn plus 1. So it's the pressure at the new time step that makes the new velocity at un plus 1 to be divergence free. That is the typical way, and I think also in the lecture notes we write it in that way. So that this would be Pn plus 1, and then of course it would be n plus 1 here, n plus 1, and n plus 1 here. That would kind of indicate that we have an implicit pressure treatment. I would just like to comment here. It's not extremely relevant, but I just want to comment on the fact. Well, it's not that the pressure that you calculate in that way is actually not the pressure at n plus 1. It is that pressure that integrated over the whole time step renders the velocity field divergence free at the end. So in some sense, you should consider it as being the average pressure over the whole time step. But I think formally we can write it's Pn plus 1. The second comment is, well, we have here a Laplace equation that we need to solve for the pressure. I mean, this here is the Laplace equation, the Poisson equation, where we have the Laplace operator equaling a right-hand side. The right-hand side we all know, that's all very good, but then we need to kind of solve the second derivative. Now, of course, the issue is we need to know what the boundary conditions are. So we need to, in principle, have boundary conditions for the pressure. And this was something that also you discussed with Ardish here. And it's not so simple to actually find pressure boundary conditions. It's actually very much not simple to do so. And we could spend a whole lecture on these boundary conditions. For the time being, I think the easiest, if you just believe me, that for Dirichlet velocity Dirichlet conditions, the correct pressure boundary condition would be dp dn being zero. So boundary conditions, we set dp dn being zero. Technically speaking, we would not need any pressure boundary conditions. If you formulate the problem in the correct way, you would actually not need boundary conditions. But as I said, this is a kind of a more advanced topic, which one can take at a different time. So we need to specify, practically speaking, we need to specify homogeneous Neumann conditions for the pressure. And of course, that directly leads me to the next problem. Well, if you have only homogeneous Neumann conditions on the pressure, it actually turns out that the pressure level is not defined, as in homework number 5, I think. So that means you actually need to fix the pressure level. So since only Neumann pressure boundary conditions, we need to fix the pressure constant. Well, essentially, I mean, formally written, it turns out that if P is a solution, then it's also P plus some constant C of T, exactly the same. It gives the same solution of the problem, as you can see if you put that into the equation, because it's all derivatives, all the this constant would fall out. In fact, it turns out that this constant may be a function of T because there's no time derivative. So this C of T needs to be fixed in some way. And the typical way, as also described in the manual, is that you just pick one point in the domain in which you set the pressure to a specific value. There's other ways of how you could fix it, but that's certainly one way that you could do it. So fix the pressure constant in one point in the domain. Okay, well, I guess this is it. Then you have calculated the new velocity, and after step number 5, well, you go back to step number 1. You calculate again a new nonlinear term, a new viscous term, a new forcing term. You calculate the intermediate velocity, you calculate the pressure, you correct the pressure, and you go on. So this is how you would time integrate. Okay, do you have any questions regarding that? Okay, but then I guess we can look at the second part, and that is the discretization. So we have now looked at the numerical method. Let's now look at the discretization. Well, so how do we discretize our domain? Well, first of all, let's now consider, and I try to sketch here something. Let's consider that this is our domain that we would like to look at, so a rectangular domain with a boundary as indicated here. Let's make one example where we would like to use kind of a specific, distribution into what is called cells in this way. So that we have 3 cells in the vertical direction, and I try to get 5 cells in the streamwise direction. So this would now be our domain. So the walls or the boundaries are like this. Well, like this, and then this is my interior. Now, as I was saying, we have a coordinate system that we can do like this, that the origin is down here, and this I would call the x direction, this I would call the y direction in a classical way. I would also then, as we introduced before, I would have a first index I, which goes in the x direction, and in the y direction, I would have my index j. That would mean if I now just go, these little squares would be my cells. I would now say that this is cell number 1, this is 2, this is 3, this is 4, this is 5. Here it would be 1, 2, and 3. So in this case, now if I'm having it like this, I would say that nx is 5 and ny is 3 as the number of cells. Okay. So now I have defined I have distributed my domain into cells. But the next step is, since we are going to use a staggered mesh, as Ardashir was already introducing, we also need to know in what points we actually define our velocity components and the pressure components. And the idea now of the staggered mesh is that actually these positions, or the velocity components, are not all defined in the same physical place. They're all related to the same cell or element, but they're not in the same physical place. And it turns out that the way we do it is that these squares here, these would now correspond to the positions where the u velocity is specified. So this would be the u velocity. And if I'm taking triangles now for the v velocity, the v velocity would be in these positions, like this. And well, do it like this. So this would be the v velocity, and the pressure would be defined in the cell centers. So this would be the pressure. So that's the standard, or the way that we would distribute now our something like this. Well, that of course also means that suddenly we have actually a different number of u, v, and p unknowns. Now for p, it's maybe the simplest. There we have exactly nx times ny unknowns. For the u velocity, on the other hand, well, there we realize that we have one more in the x direction. So we have nx plus 1 times ny, red squares here. And we have, if we think of the green triangles, well, we have 4 times 5. So we have nx times ny plus 1 triangles. Okay, but now having said this, you actually realize that some of these red squares, they actually lie on the surface, on the points where I actually have a Dirichlet boundary condition given. The same thing here for the triangles. The ones that I'm filling now, these are the ones with boundary data. So this, for instance, that would have boundary data. So that's part of the boundary condition. So that means, in fact, the filled squares, the filled triangles, they are not actual degrees of freedom of the problem. So that means that in fact, what it means for u and v is that instead of having nx plus 1, it will actually be nx minus 1 degrees of freedom and ny minus 1 degrees of freedom in V. The other points, they are actually boundary conditions. So that means that it's quite important for you to realize that if you, for instance, in the MATLAB code, define nx and ny, so in MATLAB, nx and ny, these correspond to the number of cells that you have. So in this case, 5 times 3. But at the same time, if you initialize the u velocity field, so let's just do an example. If I would like to initialize that with zeros, I would need to initialize it in this way, that this would be nx minus 1 and ny, whereas the v velocity initialized would be nx and ny minus 1. The pressure, on the other hand, would be exactly nx times ny. So that's just important to keep that in mind in terms of the data structure that we have, that we only store the degrees of freedom in u and v. So that means those values that are calculated. The boundary conditions as such, they are included in something that we call the extended mesh. And in the code, we call it UE and VE. And that is the mesh essentially where we add one layer around it where the boundary conditions are imposed. So that is with the boundary conditions. There is one more aspect that I think is important that I would like to highlight here. It's written, of course, also in the manual, but I think it's important enough that I just mention it. And that is about the kind of the orientation of the data. Now, physically speaking, this, of course, as we have indicated here, that is the way that we perceive the cavity. So we have the x direction to the left, to the right, and we have the y direction up. But if we use in MATLAB the indices I and j, the way that is written here, that means that the first index of the matrix U is the one that we consider to be x, and the second one is the one that we consider to be y. Now, the standard way of a matrix notation is, of course, that I would vary like this, and j would vary like that. So the first index in a matrix would always go down, and the second one would go to the right. So that means if you kind of want to get the physical correspondence between the matrix and the coordinates, you would actually need to consider the transpose of the matrix. So what is actually stored is the transpose of u and v and so on. So that's just important to keep in mind that in the way that we think the coordinates and the velocities are stored, the first index is x and the second index is y, which is the opposite as if you would kind of just store it in a matrix. Okay. Yeah, so that much about the notation and the data structure of how things are stored. So whenever something doesn't work or you get a wrong index in your code, try to think of how big a specific array needs to be in terms of nx and in terms of ny. Think of this figure here and count, whether you need to have whether a quantity is defined on an edge or in the center or whatever it is. So that's the kind of the way that it is defined. Okay. Now, let's now maybe move on and try to see whether there is any difficulty in calculating some of the terms that we have indicated here with steps 1, 2, and 3 in the whole procedure with the fractional step method. So the first thing we need to realize that if we solve the U momentum equation, so the one in X, then this equation needs to be written on the points where the U velocity is actually defined. So we would like to have all the quantities here defined in the U velocity points. So that is the points where the U velocity is defined. So that's the points that lie between the cells in the X direction. And the way that we annotate that is that we say that if this, for instance, would be point I, and this is I plus 1, then we would call this point in between to be I plus 1/2. So that's the kind of the middle point between I and I plus 1. So the X momentum equation is always solved on I plus 1 and J at those points. Similarly, the vertical momentum equation is solved at, if this is point J and this is J plus 1, it will be solved at J plus 1/2. So that's an important notational issue that we know if we write it down as an equation. But keep in mind, when you look at the index in MATLAB, of course, we cannot have half indices. So there, the half indices are again kind of moved by half back into integer indices. But if we write down what points we want to, add or subtract with, then we need, of course, to use these half steps. Okay, so how do we now solve the individual terms that we want to or that we can calculate? Well, I guess if we start with I guess the most important point would be the second derivative, or the convective term, which we want to calculate. And for that, we actually need to understand what or how to move between the, where is the mesh? How we can move between the squares and the circles. Let's now look at how to calculate the convective terms. I would like to do that with one example. I would like to calculate the term duv dy as an example term. That is duv dy. That's a term that appears where we have the equation. That is just one term in the streamwise momentum equation. So that means if I sketch it kind of a little bit bigger, but not like this. So if this is my mesh, my cell mesh again, this is part of the streamwise momentum equation. So that means I would actually need to calculate it in this point here, because it's part of streamwise momentum. So I need to calculate that in a velocity point. And so this would be point I. This is I plus 1, and this is maybe I plus 1/2. So that's where it needs to be calculated. So how would I do that? So I need to and this would be J. Now for this term, I realize I need to calculate, so the outermost bit here is to calculate a derivative in y. So that means the last step would be to somehow do finite differences in y. Now the typical way to do that in our simplest approximation is that we would like to do finite differences between this and this point. So where we have a spacing of delta, how do I write it? Delta x or hx or hy rather. Hy. Okay. So that would now mean that that I would need to calculate somehow u and v on those points here to be able to do these finite differences. Now the issue is, as we know from above, that the u velocity is defined on the squares. So the u velocity is essentially defined here. And the v velocity is defined on the triangles. So here, here, and here, and here, for instance. And now if I want to calculate the u and v in this point, I need to somehow, find a way of going from this triangle and this triangle to this one here. So I need to somehow do an average between these two cell values to get that value. At the same time, for the u velocity, I also need to do an average between these two values to get the u value in this point. And once I have then the u and v at these center or these corner points, I can then do the finite differences in the vertical direction. So that's essentially the idea of how I would calculate now the term du, duv, dy as part of the streamwise momentum equation. So as this term here. So that means first I need to do an average of the v velocity in x, an average of the u velocity in y, and then do the finite differences between this point and this point. Now, the basic idea how to do that is that we use something that is called an averaging operation. And that is actually implemented also in the MATLAB code. It's called AVG, and it does nothing else than just averaging two neighboring velocity points to give the average in the middle. Now, this can be used to define what I would call an averaged mesh, so UA and VA. This is based on an averaging operation, AVG, applied to the velocity field. And now I'm taking the extended one to also include the boundary conditions, and I also include here the extended mesh. Now, the second index in this averaging operation is the direction in which I would like to average. And it takes two parameters, 1 or 2. 1 means that I average in the x direction, and 2 means that I average in the vertical direction. Now, in this case, I want to get u averaged in the vertical direction to get this point. So I will have the value 2 here. And for v, I want to average in the x direction. So I'll put index 1. So with this newly defined UA and VA, the averaged mesh, so the mesh that is defined on the cell corners, I can then very, very easily just evaluate my my terms. So for instance, I can write UVY as a variable in MATLAB. I mean, if I want to now do this term, I can just simply write, well, uvy would be 1 divided by hy times somehow a difference operation. And in this case, I can also use a MATLAB function which is called diff of UA multiplied pointwise with VA. And now I need to give some parameters here. Namely, I want to do the first derivative. For the diff operation, I want to do the first derivative. And in this case, I actually want to do the derivative in the vertical direction because I do it in y. I would need to write comma 1 here. So that's now shorthand for exactly what I have described here. First doing the averaging, and then doing the difference in the vertical direction. Of course, in the same way, you can also calculate UVX, for instance. That would be the term that is relevant for the where do we have it? That is this guy for the streamwise, for the vertical momentum equation. Also there, the thinking is exactly the same in a sense that now, because we're in the streamwise, in the normal momentum equation, so that means we actually need to get the result in this point here. So that means we actually need to get the derivative between this corner point and this corner point. Right? So otherwise, it's the same idea. I do an average of u in the vertical direction, an average of v in the streamwise direction. Now I just take the derivative in the x direction. So that means that would, for instance, be 1 over hx times diff of ua times va. But actually, there was something wrong here, of course. This one should have been 2 here, of course, because it's the derivative in the vertical direction. Sorry. So because here it's 1, 1. So because it's the first derivative and it's in the x direction. So in this way, you can then consistently define all the derivative operators that are needed to be calculated. Okay. So this is the way of how to calculate the nonlinear terms. In the same way, you can then also calculate the diffusion terms. Also there, the idea is you would need to, based on the neighboring points, you would need to calculate the derivative of the derivatives. So if I just do like this, so the viscous terms. Also here, if I just sketch a mesh. So if I want to calculate, for instance, for the streamwise momentum equation, so this is my streamwise momentum equation, or the points where the streamwise momentum equation is defined, and I want to calculate the derivatives, for instance, in point. If I do it in x, so this would be index I. This is I plus 1/2. This is I plus 1. Well, the derivative in this point would then essentially be a central difference between these 2 points. So something like that. And of course, in the y direction, it would be kind of like this. What you can realize here is for the diffusion operators over the viscous terms, there is no averaging necessary because the points directly exist in the correct places. So just to give you an example also here, if I want to calculate the viscous term in the u velocity, that would then in MATLAB language would be diff. Again, this diff operator from MATLAB. It would be the array UE, and it would be the second derivative and in the first direction plus this, the derivative of UE, but then in the other direction, so second derivative in the Y direction. As simple as that. Actually, here would be 1 over hx squared and 1 over hy squared. Something like that. Okay, so that's the way how you would calculate the viscous terms and the advective terms, keeping in mind that you're doing everything on a staggered mesh. And really, the important thing to realize is that if you operate on a staggered mesh, the U momentum equation is always solved on the U points, and the V momentum equation is always solved on the V points. So you need to formulate the equations such that they kind of take that they have the right size, that they operate on the right equation. There is one aspect that I will not have time now to discuss, but it's actually described quite extensively in the manual. That is how to implement the boundary conditions. That is in the step when you go from the U velocity to the extended mesh. To the extended mesh UE, where essentially you're kind of to put a ring around with additional velocity values. And the point there is that if you now do it, for instance, for U, that means that on this wall and at this wall, there is no problem. You could just add those points. But for instance, at the upper wall, it's of course not so simple because you only have U velocities given here, but no U value here. So what you do is you have the value given here, but here you have no U point. So what is done is that you introduce one row of points which actually lie outside of the domain, which are then the boundary condition points in the at this boundary, and you calculate the value of this point such that the linear interpolation between this and this point will fulfill the correct boundary condition. So this is then what is called a ghost point, as also indicated in the manual. I can maybe write it down. So extended mesh using ghost points. Okay, I guess that's more or less it. What I can say about the actual project. Most of it is described in the extensive manual. All the various steps with also small examples for different parts that we can write as a code. So I would say, let me know if there is any questions regarding the implementation, and then I'm very happy to, of course, provide more insight. Other than that, just read the manual, and together with that, it should be quite straightforward to then implement it. So this is all I wanted to say for today on how to implement things in the MATLAB code. So I would like to close for today with that, and just remind you again that tomorrow will be the OpenFOAM introduction with Fermin. So until then, try to get a virtual machine running on your computer so that you can run a Linux with OpenFOAM. And then on Thursday and Friday, we have 2 hours each again. On Thursday, I would like to answer questions, which can be about the project or other parts of the course. And if there are no questions, I have some additional material that I can go through. And on Friday, we will have 1 hour together on evaluating the project, discussing some aspects of the project, and then also homework number 6, the second hour. Okay, with this, I would like to thank you for today, and I'll be around for additional questions, of course. Thank you very much.